Oh, how about now?
Yes, I think, yes. Yeah. Okay, perfect.
Okay, all right.
Yes. Thank you.
Okay. I'd like to introduce recent research activities in my group, which use various techniques, including neutron and X-ray scatterings. So before I move on, let me show you where I am. It's a bit away from Indonesia now, but KAIST is located in Daejeon, which is about 150 kilometers south from Seoul. In Daejeon, there is a Korea Atomic Energy Research Institute, which has Hanaro Research Reactor. To the east from Daejeon, there is a Pohang, city of Pohang. There we have a synchrotron radiation source, and recently installed X-ray free electron laser as well. So this is a view of KAIST. It does not look like this. This is taken sometime in spring, I guess. But we have about 11 to 12,000 students. About 5,000 students are undergraduate, and rest of them are master's and PhD students. And also we have a little over 600 faculty members, and currently KAIST is trying to recruit new faculty members aggressively, including our department. So this number is maybe a bit higher than it is shown here. And this is a Google view of the city of the Daejeon. KAIST is here, about 5 to 6 kilometers away, which is about 15-minute drive from KAIST. There is a Korea Atomic Energy Research Institute, and then which has a Hanaro Research Reactor. So this Hanaro Research Reactor is a 30 megawatt research reactor, which became critical in 1995. And since then, they put the various thermal neutron scattering instrument around the reactor. And also they have a cold neutron facility, as shown here. And the large space here is reserved for future beam lines to for upgrade. So Abby was here when there was a conference and meetings here. Yeah. And this is the photo view of Hanaro cold neutron facility. So vertical reflectometer, and then this prompt gamma activation analysis, and this 40-meter small angle neutron scattering, which I was involved as a PI for this one when was it developed. So our group mostly use this instrument here, and then disk chopper time of flight, which measures inelastic scattering to see the dynamics. And we have ultra small angle scattering, and then also cold triplexes as well. So it was down for some time due to this some seismic issues to enforce the wall around the reactor. Now it is back to operation. So hopefully we can use more this instrument more often. This is the view of Pohang light sources. We have there is a PLS2, which is upgraded version. of the synchrotron, which has a 3 giga-electron volt accelerator, and then on the left-hand side, very long straight, which is about 1 kilometer long, is the X-ray pre-electron laser. And then this accelerator here can produce maximum 11 GeV beam. And then you produce a hard X-ray and also soft X-ray. So for each, you have they have four different instruments. And PLS2, the synchrotron source, has a large number of beam lines. It's about 36 beam lines are operational. And then our group mostly use small angle X-ray scattering because, and also sometimes X-ray absorption spectrometers. This is the brief introduction of the neutron and synchrotron facilities in Korea. There is another activity which is going on, is that to build another synchrotron source near Daejeon area. We are looking forward to have it soon. So now let me talk about the research activities in my group. As we all know, all the materials we have consist made of atoms on this periodic table. And then depending on what kind of atom is used or how the atoms are placed in space. So depending on symmetry of this crystal, they all have a different properties, as we all know. And now, these days, over the last 10 to 20 years, synthesis of nanoparticle has been developed quite well. And then now people can produce very monodisperse nanoparticle. This is one example we prepared in our group. So now we can consider this nanoparticle as a new building block, well-defined building block. So you may consider this one just like an atom, but which is much, much bigger than atom itself. So you can consider it sort of super atoms. So these are the another example, spherical gold nanoparticle. As you can see, they are fairly monodispersed. Not only spherical, this is the so-called cuboctahedron. It's like a Lego block for play with. This is the gold cuboctahedron gold nanoparticle. In fact, the one who developed and made this particle is Amina Uma, who was my former student. Now she is in the university chemistry department in University of Indonesia, and she also find a way to make a different shape of cubocta nanoparticles. This is rhombic dodecahedron, and also this is octahedron. This is a very beautiful nanoparticle. So we have. So having this kind of things, not only by us, by many groups in the world, people can make various kind of nanoparticles with different shape and size. So now we can think of a sort of periodic table of nanoparticle. Since nanoparticle can have, we can control the size of nanoparticle. So in principle, we have a three-dimensional periodic table, which in principle, which provide much wider opportunities of making different materials than atom itself in principle. So now if we can use this nanoparticle as a building block, and then if we can make a different combination of nanoparticle with a different symmetry, so then this nanoparticle will have some coupling as as the atomic coupling in the atomic crystal. So we may be able to have new properties in chemical and optical and electrical and magnetic point of view. So this is the basic concept. So this is one example of a nanoparticle superlattice in nature. This is opal, which made of silica nanoparticle. It shows a beautiful color. So the reason why it shows beautiful color is due to the diffraction of the light at the different angle. So these nanoparticle superlattice can be used various purposes. For example, molecular sensing using surface enhanced Raman spectroscopy, or if you use a quantum dot to form a superlattice, it can be used as a light source. Or if we use metallic one, so plasmonic photonic crystal can be made. Also, by properly patterning these nanoparticles, maybe very thin, ultra thin focusing lens may be also prepared. But still, this is been an early stage. So the coupling between nanoparticle superlattice is still under investigation. There will be a new possibility of very new opportunities. But question is, how to synthesize nanoparticle superlattice? There has been various studies using electrostatic interaction or solvent evaporation or deep stabilization method and so on. These are form of very beautiful structures. And also another interesting way of preparing this superlattice is using DNA. DNA, as you know, it has a specific binding. Yeah, G bind to C, A bind to T. So by using this one end group, which is attached to nanoparticle surface, we can program the particle. So this Z particle combined with Z particle only due to this sequence. And this X particle in this case is only bind with Y particle, which is a conjugate series of this sequence. So based on this, people can make beautiful structures. Now, being in the soft matter side myself, we are asking whether soft matter can be used for preparing nanoparticle superlattices. So, for example, using block of polymers, surfactant, and so on. So the basic concept is to prepare a particle and functionalize with some molecule which has a specific affinity to specific region of this template, for example. So red one goes to red area, blue one goes to blue area. That's the basic concept. So these are the studies people have been doing. Yeah, nice ordered structure, but it's not necessarily crystalline structure. It's sort of a well-patterned structure, you may call. So can we do better than this with the soft matter? So you considered Micelle as not just a template, as an actively participating object in superlattice formation. Yeah. The reason why we consider the Micelle is that, especially surfactant Micelle, is that surfactant micelles are highly monodisperse objects, And also it can be it can have a interesting behavior, like a stimulus response. So pressure, temperature change, their structural symmetric transition may occur. So this is an idea we start with. First, this we consider the one-dimensional object. So we considered this cylindrical surfactant phase, which forms a hexagonal lattice. And then combine with mix with one-dimensional object here. In this yellow particle is a carbon nanotube is covered with surfactant. You can consider this as a 1D object. And this one has a slightly different, larger diameter, and then this surfactant cylinder. So we performed the SOX measurement without the nanotube included. Of course, we form a hexagonal phase with this symmetry. And then if we add nanotube into the system, it looks very similar, but as you can see here, there is a new peak here shows up as well. And then also it has a specific relationship 1 square root of 3. These two peaks has this specific relationship. Okay, so what is this origin of this? To understand, to see the origin of this new peak, we did a small angle neutron scattering. Okay, basically question is where these new peaks comes from is so to see that we did sort of contrast variation experiment. Basically, this neutron, deuterium, and hydrogen has a different cross section. So the H2O and D2O has a different color from neutron point of view. When this surfactant R molecule, which contains a lot of hydrogen, located in put it into D2O, you can see very well. But if you properly mix the D2O and hydrogen H2O, we can make this surfactant invisible from neutron point of view. Okay. So this is the data to find where these particles, surfactants are invisible. Now, after preparing this condition, we can put this yellow nanoparticle. Then we can see where these nanoparticles are located. So we are looking at the only nanoparticle. But since this nanoparticle is also covered with surfactant, which is very similar to this micelle, instead of using hydrogenated surfactant around this tube, we used deuterated surfactant around this tube. Then you can see this particle location very clearly. So this is the contrast matched small angle neutron scattering. So all these yellow to blue tubes does not visible, only just yellow tubes are visible. So as you can see here, this new peak is come from yellow tube, nanotube. So basically the structure is this. So hexagonal array. This yellow tube form a hexagonal array, which is embedded in this honeycomb symmetry, honeycomb structures of this blue tube. So they do this to maximize sort of pre-volume entropy. The main reason is due to these size ratios, differences. And then we go further. What if we change the diameter of the nanotube, yellow tube, meaning the size diameter by controlling diameter ratio between these two tubes? We try to see how they are changing. So this is the without the yellow tube. Now by adding yellow tube of different size. Here, number is the diameter radius ratio, size ratio. As you can see here, where there is a phase transition temperature is also changing, which also not only depends, but one thing I'd like to also see is that always they have a new peak. Same thing, which is interesting, but not quite exciting because they don't see any show any differences. So now we go a little bit further. Here we kept the amount of ratio of the nanotube same, but here we try to put this same particle but with a different amount. Here 10, now here 5 nanoparticle with different amount. Now as you can see here, there is a difference show up here. Okay. And then instead of 1 to scale root 3, now 1 to scale root 2. So there is some symmetry changes. Then we also confirmed with the neutron scattering that the origin of this peak is also due to this yellow tube. Okay, so by slowly controlling the amount of this nanotube, it starts from this structure up here, and then which is a honeycomb array in hexagonal array in honeycomb lattice. As we decrease the amount of nanotube, yellow tube, then it goes to hexagonal array in Gakomi lattice, which is very also interesting. So this is actually mixing one-dimensional nanoparticle of 2 different diameter. Usually doesn't form these superstructures. They usually phase separate. But by using this surfactant system, model system with the nanotube, we show that in fact this 1D object, by properly controlling, we can have binary superlattices with a different symmetry. Now, let me skip that. And now question is, can we use this kind of approach for solid nanoparticles? For example, inorganic nanoparticles. For example, gold nanoparticles. So we try the spherical micelle system as basis, because we would like to demonstrate that one with the spherical gold nanoparticles. In fact, we also consider the gold nanorod as well at the beginning, but nanorod diameter is too much bigger than the cylindrical surfactant system. So we did try to this gold nanoparticle. Here, this surfactant system, C12E25, form a spherical micelle and then body-centered cubic symmetry in this region. And these nanoparticles, gold particles, are functionalized with polyethylene glycol. Essentially, this functional group is the same as PEG here outside of the surfactant. So you may consider this one as a binary mixture of the 2 spherical particles, or you may consider it a binary mixture of the micelles of different diameter. In these cases, diameter of nanoparticle we used is 3.7 nanometer, and we used 2 different sizes of the molecule. One is the short one, 1 kilodalton, and then another one is 2 kilodalton functional group attached with to the gold surface with the diol group. Okay, the size ratio here is 5.59 0.573. And this is the overall size of my cell. This is overall size of the nanoparticle. Functionally is with PEG. So without the nanoparticle, my cell itself shows a BCC symmetry, as it is clearly seen in the SOX data. Now we included the nanoparticle functionalized 1 kilodalton PEG. Dramatic change in scattering pattern. It's a lot of peaks shows up like atomic diffraction pattern. Okay. And this is depending on amount of nanoparticle we put it in. Essentially, they show the same structures, but this one has a highest sharpness of the scattering pattern, meaning that highly ordered. And another thing, now if you to the same surfactant system, if you add this nanoparticle with a longer chain, it also shows very sharp scattering pattern of different symmetry. And then if you increase at some point, there is also some change in scattering pattern as well. So looking at these data more closely, and after correcting particle form factor, this is a scattering pattern, structure factors. This is like atomic diffraction pattern, but this is the nanoparticle cases, diffraction coming from arrangement of nanoparticles. By indexing this one, we find that this is the structures, binary structures, which forms Mg zinc 2 type structures, very clearly. Not only the peak position, their intensity matches very, very, very well. And for the PEG2 particles, this is indexed with AB13 structures, sodium zinc 13 structures, which is highly ordered. Now, PEG2 at the 46% amount ratio, it is not the percent, it's the amount. And then it form ALB2 structures. In fact, these cases, there's a mixture of ALB2 and zinc 13 structures, these structures. So, in fact, then how can you explain these structures? In fact, we first consider the hard sphere binary mixture, and then this is a particle size ratio. This is well reported that when for the phase diagram, depending on the size ratio, when the size ratio is 0.5 to 0.61, ALB2 structure is the minimum, the structure to form, to minimize the entropy of patching volume and pre-volume, and to minimize the pre-volume entropy, this structure is preferred. And size ratio is in this range, it is zinc 13, AB 13, and this magnesium zinc 2 type structure, depending on these structures. In fact, if we use our cases, yeah, they are reasonably well matched with this condition. So we can say that the even though our particles has a soft shell, at this condition, they more or less follow a hard sphere models. Not necessarily all the soft particles follow hard spheres, depending on the thickness of shell and then softness of this molecule. I mean, in other words, softness of the particle. Some particle does not follow this hard sphere model, but in our cases, we found that they follow hard sphere models. And since these particles are mixtures are mixed with the Micelle system, this system can be sensitive to external stimuli. We tried to change the temperatures depending as we increase the temperature, it goes isotropic phase, and cool it down back, it goes back to this original symmetry structures. So this is the first actually example of all the actually this is the thermally reversible all the disorder. Okay, it's not the first example. All the disorder was reported before, but if we tried this APG2 type nanoparticle, which has a longer shell, and this one goes from, if you cool it down, increase the structure temperature, then it changed from sodium zinc 13 structure to AlB2 structure, and cool it down, it comes back. So this is a demonstration of the first demonstration of thermally reversible order transition in nanoparticle superlattice. The reason why, of course, we can have this thermally reversible transition is due to the Micelle system, which we use as a component of this. Okay, so in fact, our study is well matched with Gibbs free energy calculation, which was reported some years ago. Actually, this phase diagram is the x-axis composition, y-axis is expressed as a reduced pressure. Temperatures goes here. So in fact, we are changing to this way, and there's a transition, which is qualitatively well matched with this phase diagram for hard sphere system. And this cases also follow this phase diagram. So okay, so this is the sort of summary of this micellar system cases with gold nanoparticles, spherical gold nanoparticles. So we can, depending on, by controlling the size ratio, in these cases, by controlling this molecular length on the surface, we can form a beautiful, highly ordered superlattice of different symmetry. And then they are, their symmetry structures, crystalline structures, can be controlled by controlling temperature. Now, another approach we are trying to do is, okay, why don't we use just a nanoparticle interactions? People use the slow evaporation, and also people use the DNA and also. But what if we use some chemical bonding to form different structures? So this is an idea. So one particles are functionalized with the so-called MUA, which is this COH functional group. Another particle is functionalized with this group. And then, in fact, this functional group at the end form covalent bonding. If we put some proper catalyst in. So means these two particles are connected to this. So covalent bonding. It's like atom make bond with neighboring atoms. It's like a nanoscale version of atomic bonding, you may call. So we use this. So we can do two different ways. If we put summarize AA type, same type, some molecules form a AA type reaction, then you form a FCC if AA type. interaction. If A, B type, meaning that A only bind to B, not A itself, not B itself. Then if you mix them together, it has to form a BCC structure. Okay. So in a way, we can, in this way, we can program the formation of these nanoparticle superlattices. So here, people have been using solvent destabilization, evaporation, or destabilization, or DNA mediated. In fact, particles are interacting basically in this method intermolecular forces. Yeah, basically hydrogen bonding, for example, for DNA cases. So, which is very nice. But on the other hand, the binding force is rather low. So meaning that it can become easily unstable. For example, DNA cases, DNA binding is maintained only in water, saline water, at a certain temperature. If the temperature goes like 60, 70, it is bind, denaturization, binding is destroyed, meaning that superlattices is destroyed. So, but on the other hand, covalent bond is much stronger than this previously used interaction. So it can be provide much more stable superlattices. So this is our first, our group proposed this concept first, we mean covalent bonding approach. So this is the system I just showed you previous slide. So we use this anhydride formation reaction. So this is the anhydride formation reaction, which between the ligand functionalized on the surface of the nanoparticles. In this case, it's gold nanoparticles we are using. So we use the 8.3 nanometer gold particle, which is also very monodisperse. So here we mixed these two type of nanoparticle in the solvent, which is water and DMF 1:1, and at the different pyridine concentration. So pyridine is the sort of catalyst to enhance the reactions. After some time, this particle interact each other and then precipitate. So we put this precipitate into the SOX B9, and we found a very nice scattering pattern here, which shows FCC symmetry. Okay, FCC symmetry. And also by using FTIR, we confirmed that these anhydride bonds are actually formed in this structure superlattices. Okay. So this is a scattering pattern to show that actually very nice superlattice, gold nanoparticle superlattices. Here, same size of gold, 8.3 nanometers. These are the SEM images. Okay. So made of gold. Very nice superlattice, which is a few micron size. Okay, of course there is also some defect, and these by looking at this, they are growing layer by layer. So this is add atom like single particles are around in here, and then this particle mostly goes to this edge, which make it more stable. Coordination number increase when they go to here, and then grow one layer, and then on top of that another layer goes on. This is a SEM image of the superlattice of gold. And if you look a bit more closely, yeah, this is the nanoparticles. As you can see, that nanoparticles are form a very nice superlattices, and then this one atom. This is atoms of a single nanoparticle here, and there is a seed, and then this will grow into something like this one. And also, since these nanoparticles, superlattices, are formed with covalent bonding, unlike DNA cases, unlike solvent, unlike the superlattices formed by slow solvent evaporation, these superlattices are very stable in solvent of different polarity. So DNA cases, DNA method, and solvent evaporation method, if they put things into the solvent, their structures are usually destroyed. So in our cases, they are very stable because our particles are connected through chemical covalent bonding, and also stable roughly about 160 Celsius. Of course, it cannot go too high because these particles are covered with organic molecules. Organic has a molecule has a certain stability. If you go further, their structures will be destroyed. Okay. But compared to DNA, which is only stable around 50 or 60 Celsius, this is much better thermal stabilities. Okay, so in summary, I think micellar system and also covalent bonding reaction can be a very nice approach to form nanoparticle superlattices. For the micellar, with the micellar approach, we can have a very ordered, but at the same time, stimulus-sensitive nanoparticle superlattices can be used. And with the covalent bonding approach, we can have a fairly stable nanoparticle superlattices. So for the moment, we have demonstrated with a single gold nanoparticle only, but we are also in the process of using forming binary structures, meaning, for example, one particle is gold, another particle is semiconductors, and so on. Then also we can consider one is gold particle, another one is magnetic particle, and then we can have different properties and for different applications. So by having this way of making good quality of superlattices with good control of their symmetry and also their lattice parameter will provide us a very new opportunity to study new properties and possibly new application of this system. These are my group. So these are the students who have contributed and also postdoc who have contributed for this work. Thank you very much for your kind attention.